Alright, what's up guys? We are going to be doing a circuits 2 problem. This is going to be an RLC circuit. We're going to do transient analysis on this. So as you can see, we have this 5 ohm resistor and you have this switch. It's going to go, we'll call this A, call this B. It's going to go to switch to B at t equals 0. We have a 0.1 farad capacitor in parallel with a 2 ohm resistor in parallel with a 1.6 Henry inductor. So we are going to go ahead and define some quantities. Let's call this current through the inductor IC of t. Let's call this resistor current IR of t, and let's call this inductor current IL of t. And let's define this voltage drop over here. We'll call this V of t. So the first thing that we want to do is go ahead and find alpha and omega naught to determine if we have underdamped, overdamped, or critically damped circuit. So for a parallel RLC circuit, alpha is equal to 1 over 2 RC. So this is going to be equal to 1 over 2 times 2 ohms times 0.1 farads. And this is going to get us 2 times 2 times 0.1. This will get us 2.5 nebers per second. And then for omega naught, it's going to be equal to 1 over LC, all square rooted. So we have 0.1 farads times 1.6 henries. All of that's square rooted. So 0.1 times 1.6. This is going to be 2.5. 2.5, this will be radians per second. So now we compare the two, and since alpha equals omega naught, we have a critically damped system. So that's just going to help us define these equations later down the line. So we can go ahead and evaluate the circuit at t equals 0 minus. We have the 12 volt voltage source, this 5 ohm resistor, and we are just going to have this capacitor here. But in DC steady state, the capacitor is going to behave like an open circuit. So we can recognize that this is still going to be V of 0 minus, and this will be IC of 0 minus. Let's go blue. Right, so we can see that V of 0 minus, we'll come back to that in a second. And IC of 0 minus is going to be 0 amps. That's just because of the definition of the open circuit. There's going to be no current flowing through there. And then IR of 0 minus is 0 amps, and IL of 0 minus equals 0 amps. Because if that switch is in position A, then there's going to be no current flowing through that 2 ohm resistor or that inductor. And so what about this voltage drop? Well, since this is an open circuit, there is 0 amps going through here, 0 amps going through here, so there's no voltage across this 5 ohm resistor. So the voltage drop here is just going to be the 12 volts. So we have 12 volts. And then let's get some more space. We're going to look at t equals 0 plus. Now we are going to have just the capacitor in parallel with the 2 ohm resistor in parallel with the inductor. However, the voltage across the capacitor cannot change instantaneously, so we're going to replace that with a 12 volt voltage source, which is connected in parallel with this 2 ohm resistor, and then also with this 1.6 Henry inductor. And current through an inductor cannot change instantaneously, and since at t equals 0 minus, it was 0 amps, we have to do an open circuit as opposed to a short circuit, which we would normally do, to keep the current 0. So we would have V of 0 plus, we'd have IC of 0 plus, IR 0 plus, and then IL 0 plus. So V of 0 plus is still going to be 12 volts. IL of 0 plus is still going to be 0 amps. So since this is an open circuit over here where the inductor was, all that current is going to run into the loop with the 12 volt source and the 2 ohm resistor. Right, so current is going to flow in that direction. So IR of 0 plus is just going to be 12 volts over 2 ohms, which is 6 amps. And then the way we define the currents at the beginning of the problem, IC is just in the opposite direction of IR. So IC of 0 plus is minus 6 amps. And so so we want to write equations for V of t and then IR of t. So from the table, for a critically damped system, V of t is going to have the form A1 t e to the minus alpha at plus A2 e to the minus alpha t. So we can go ahead and plug in our initial condition, V of 0 plus. This term is going to go to 0, and this term is going to go to 1, so we would just have A2, but V of 0 plus is 12, and then so we can go ahead and set up another relationship for A1 and A2. So we can go ahead and use a derivative-based relationship. So what we can do is go ahead and use something that has dV dt. And so we can go ahead and use the current through the inductor. So we have I of C, right, it's C dV dt. So this will be 0.1, and then from the table, the derivative is minus alpha A1 t e to the minus alpha t plus A1 minus alpha A2 e to the minus alpha t. But we also have our initial condition for I of C. So we can say I C of 0 plus, right? We can still have this 0.1. This term is going to go to 0. This term is going to go to 1. And so we just have A1 minus, we already found alpha 1 earlier. Alpha was 2.5, and then we found A2 is 12. And this equals IC, which is minus 6. Solving for A1, you get minus 6 over 0.1 plus 2.5 times 12, which equals minus 30. And then, so therefore, V of t equals minus 30 t e to the minus 2.5 t plus 12 e to the minus 2.5 t. And we will confirm this with LT Spice after we find IR of t. So now we'll do this in blue. IR of t, because it is also part of the critically damped system, is going to have the same format as V of t. So we are going to have A1 t e minus alpha t plus A2 e minus alpha t. So remember, IR of 0 plus, right, this was going to go to 0. This is going to go to 1. We have A2. And IR of 0 plus was 6. And so now we want to use a derivative-based relationship for IR of t. But how are we going to go about doing that? We can, like, the derivative-based relationship for IL of t is going to be easy, right? Because the voltage drop across an inductor is L di dt. So we have to find a relationship between IR and IL of t. But remember, the voltage drop, let's see what's the green. VL is VR. The voltage across the inductor is the same as the voltage across the resistor. So we would L di dt is, right, we would just have IR t times R. So IR of t is L over R di dt. So, but this is dIL dt. So we're going to find a relationship for IL of t. This is A1 t e minus alpha t plus A2 e minus alpha t. IL of 0 plus, right, this is going to be A2, which is 0. So we have VL of t. Let's get some more space. Sorry about that, some technical difficulties. So we have VL of t. What the hell was that? Okay, it was L dIL dt. And from the tables, this will be 1.6. Right, this will be minus alpha A1E. Sorry, this will be t. A1t e minus alpha t. Plus this will be A1 minus alpha A2 e minus alpha t, VL of 0 plus, we have 1.6, this term is going to go to 0, and then we have A2 equals 0, and this term is going to go to 1. So we're just going to have A1 equals 12, so A1 equals 12 over 1.6, which equals 7.5. So therefore, IL of t is 7.5 t e minus 2.5 t plus, that's it, because A2 is 0. But remember earlier we said that IR of t is L over R dIL dt. So we need to find di dt. So this is just going to be a product rule. So di dt equals, so we have t minus 2.5 e 2.5t plus e minus 2.5t. So IR of t, we have 1.6 over 2, 7.5. This will be minus 2.5 t e minus 2.5 t plus e minus 2.5 t. Multiply all this out. 1.6 over 2 times 7.5 is 6. 6 times minus 2.5 is minus 15. So we have minus 15 E. This will be T. Hold on. T E minus 2.5 T. Alright, this will just be plus 6 E minus 2.5 T. Okay, and so we're going to go ahead and confirm these with LT Spice. Alright, so we are here in LT Spice. Sorry, let me move this. We're in LT Spice, we're going to do new sketch. So we're going to model the circuit at T equals 0 plus. Alright, so we have this capacitor in parallel with this resistor, in parallel with this inductor. We are going to line all these up. And then LT Spice freaks out if you don't put a ground. So you got to put a ground. This capacitor was 0.1. This resistor was 2. This was 1.6. And then 0. Okay. And so we had to put an initial condition. So if you go to the Spice directive right here, you do .IC. So the voltage at a capacitor is 12. And then we do Control M .IC, and the current through this inductor was 0. Going to go ahead and do this. And so we're going to do transient analysis. And so a good way to find out how many or how long you have to do the transient run for, you do 1 over alpha, so 1 over 2.5, and times 5. So this will be 2 seconds. So do run, and do transient, and do 2 seconds. And now we can go ahead and look at the voltage. And then we can go ahead and do right click, add trace. Let me look at these equations again. Let me write this one down. So IR of T was minus 15 plus 6E minus 2.5. Okay. Alright, here we go. Let's go back to LT Spice. Alright, so you're going to do minus 30 times time times EXP minus 2.5 times time. All of that plus 12 times EXP minus 2.5 times time. And bam, it is the exact same curve. So that means we evaluated this equation correctly. So let me go ahead and run it again. We're going to look at the current through the inductor, or sorry, through the resistor. Add trace, and we're going to check our other equation. I'm going to do minus 15 times time times EXP times minus 2.5 times time plus 6 times EXP times, or minus 2.5 times time, and bam, the exact same curves. That means we did this correctly. So this was definitely more of a pain, mostly just because we couldn't find the resistor current directly, because we couldn't find a derivative-based relationship, but we did with the inductor current. So thank y'all for watching, and hopefully this helped you.